All right, so today I would like to consider the idea of a surface integral. Now, what we've kind of been covering recently is the concept of a parametric surface. So we could take any sort of input from some planar domain, some laminar domain, and we could take that input to be, I don't know, a theta phi space or a UV space as kind of our coordinate axes. Together, these form a set of canonical coordinates, which we can use to take an ordered pair of these, and then this gets mapped to some x, y, z point, given some function f x, fy, and fz that model a point in the theta phi space to an x point, a y point, and a z point, right? So what we want to do now, or well, originally what we did is we looked at these parametric surfaces and we said, hey, how can we find the area of it? And what we determined is we could find the area by taking the sum of a series of cross products, or in the terms of a function case, we could take the integral over an area of kind of a bunch of partial derivatives squared. So you had dx squared plus dy squared plus 1. And that's kind of similar to the definition that we had for the single variable arc length function, yeah? Anyways, what we want to do now is we want to expand this idea. So say we have some surface modeled by a parametric equation. We call that surface S, script S. And then say we have some function that the surface is kind of draped over. And if we drape the surface over some function, we want to maybe determine like the flux going through that surface governed by that function f of x, which may or may not be like a vector field or something like that. Later on, we can discuss that. Anyways, given this notion, what we can do is we can make some definitions. So as always, we start with that kind of parametric definition where x is a function of uv, y is a function of uv, and z is a function of uv on some domain D in the uv space on that domain. So what we want to do is we want to define kind of a Riemann sum. So sorry for the notational difference here. If I ever just write a single integral and I just put the s down there, that's really a double integral. But just to save space, I'm just going to write one integral, but that's really a double integral over a surface. But in more advanced textbooks, they're not going to give you the specific integral. They're just going to write integral over volume or integral over space or whatever that might be. So you just write one integral. It saves you time and it saves you space. Anyways, the integral over the surface of f of x, y, and z with respect to a differential surface element is equal to the limit as m and n approach infinity of the sum from I equals 1 to m, and then the sum from j equals 1 to n of f of p sub ij delta s sub ij. Now, what does this really mean? This means we're taking a point, the function at a point, multiplying it by a little small area of parallelogram. But again, we already really discussed how hard it was to just even take a Riemann sum for a single variable function, let alone a double variable function. Now we're throwing in surfaces into it. So you really don't want to be doing Riemann sums, but it turns out there's a better way to deal with it, and it comes kind of from like that line integral formalism that we were discussing earlier. But we can rewrite this as the integral over the domain D if we write the function f in terms of that parameterized function, r of u and v. Then we can take f of r of u and v and then multiply it by that kind of magnitude that kind of is that scalar that we have attached to the differential area. Of course, that is replacing the ds, and this is replacing the f of x, y, and z. Right? So we kind of went from this arcane idea to this idea down here, which is a lot better for us. Anyways, let's try an example out, right? So I want to consider finding the surface integral of x squared ds on the unit sphere. So this is the unit sphere, x squared plus y squared plus z squared equals to 1, of course, one of our quadric surfaces. So what we'll do now is we'll set this problem up. So we have a sphere, so the obvious good choice of coordinate systems would be the spherical coordinates. So thus we can define that r of theta and phi, or r of phi and theta, is equal to sine phi cosine theta e sub x plus sine phi sine theta e sub y plus cosine phi e sub z. So what we do from here is we take that cross product, but we did that in a previous example and we get sine phi. Now what we need to do is plug it into the integral. So the integral of x squared ds is really equal to the integral over the domain D of sine squared phi cosine squared theta sine phi dA. Now what is our domain? So we're going across a whole sphere, so then phi is going to be between, or theta is going to be between 0 and 2 pi, and phi is going to be between 0 and pi. So what we'll do is we'll set up this as a double integral now. The double integral will be the integral from 0 to 2 pi, integral from 0 to pi, sine squared phi cosine squared theta sine phi d phi d theta. Of course, we have a product of functions. So this is a linear product of functions which are independent. So when these functions are independent, we can use that theorem, which says we can separate the integral as a product. So we get the integral between 0 and 2 pi of cosine squared theta d theta, then the integral between 0 and pi of sine cubed of phi d theta. Now, these are both integrals which are a bit tricky to deal with, but bring you back to Calc 2 a little bit. This integral, you can use the theorem for the cosine double angle, so you find cosine of 2 theta. This guy is a little bit more trickier. What you need to do is you need to use the the Pythagorean theorem for integrals, or the Pythagorean theorem for the sine and cosine functions. You can turn this into 1 plus cosine squared of phi times sine of phi. Then you're in a perfect position to do it like a mental use substitution if you need to. Anyways, the short of it is that you get 4 pi over 3. I explained that in a bit of a long way, but you get 4 pi over 3. Again, everything that you do here is really up to this point. After this point, you're just solving an integral, and we can solve integrals really well. I would think that we know how to do that already. But as long as you can get to this point where you have set up that integral, then you're in good shape. Because for all I care, plug it into Wolfram Alpha or plug it into Desmos, you're going to have 4 pi over 3. What's really important is setting up the parametric surface, finding the proper cross product magnitude, and then setting up the integral correctly with the correct bounds. Of course, the bound problem is not something that's going to go away. All right, so in the next video, I'd like to discuss finding these surface integrals over actual functions, and then we'll expand that to the idea of vector fields. So that's kind of where we're going with this. And we'll look at some applications of the surface integrals. But afterwards, what we want to look at is how we can evaluate. There are 2 ways that we can evaluate the surface integrals and line integrals in a much nicer way than Green's theorem or, say, this parameterization method, which would make it a lot easier. And we're going to find that the idea of the divergence and the idea of the curl are going to come into play. That they actually form the fundamental theorem of curls and the fundamental theorem of divergences, which of course will be the capstone of our project here. All right, thank you for watching, and we'll see you in the next video. We'll be discussing a little bit about finding the parametric, finding the surface integrals over actual functions in the XYZ space. Thanks for watching. We'll see you then. Thanks.